All right, AI SL2. Today we're going to do another integration rule, but it's kind of a weird one. Rather than use the calculator, I'm going to show you guys a method of how you can use trapezoids to estimate the area under a curve. Now, first thing it should be said about this, it's not an exact formula. See this symbol right here? This means that it's an approximation. The reason it's an approximation is that it uses this method, if I zoom in on this graph right here, where you take these points that are on the curve, like separated out like by a certain x distance in between them, and then you turn them into trapezoids. So that's a trapezoid kind of turned on its side, and then the next one is a trapezoid turned on its side. The problem with this is that if you zoom in real close, there's this little piece of area that's like not quite on the curve. So that's why it's an approximation. It's not perfect. But I'm going to try to break down what this formula does. If you were to take, well, first of all, the area of a trapezoid. So the area of a trap is 1/2 base 1 plus base 2 times the height. So if you look at this trapezoid right here, the base would be this section right here, and then the height would be reverse that. The section down here is the base, or the height. God, I said it again, the height. And then this is base 1, and this is base 2. So when you go to add up all these trapezoids, like you get these repeats where this section right here was the base of one trapezoid, on like the top base on one trapezoid and the bottom base on another trapezoid. So when you go to add together all these, like this is basically the trapezoid formula. It's 1/2, and then this is the height. And then these are all the bases of the trapezoids. Notice that there's a 2 in there. That's because some bases get doubled up and some don't. So the ones that don't are the y0 and y to the n. Because if you look at, I'll use a different highlighter, like all of the bases in this picture, like this one, this one, this one, this one, this one, the ones that get double counted are the ones in the middle, but then the ones on the end are just a single count. So that's why it's like the beginning base, the end base, and then all of the bases in between are doubled. That's when from A to B is divided into n intervals of equal width. Get rid of some of this diagram, it's so cluttered. Oops, I've gone too far. Okay, so I'm going to show you guys how to use this formula. Estimate the area under a curve from 4 to 12 with these values. So the first thing I notice about this is that the distance in between each of these is 2. These are like the heights of your sideways trapezoids. And then the bases are going to be these numbers, like base, 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 base. So, the area of the first trapezoid, is 1/2 base 1 plus base 2 times the height, which is 2, and this is 18. Then the area of the second trap is 1/2 13 plus 10 times 2. So each time it's like, this was the base 1 of the first trapezoid, and this was base 2 of the first trapezoid. But then for the second trapezoid, this was base 1 and this was base 2. So that's 23. And then for the third trapezoid, it'd be what, 10 plus 3? Yeah, so this is 1/2 10 plus 3 times 2, which is 13. And then the fourth is 1/2 3 plus 4 times 2. And that's 7. And then if you total all of these up, you get a grand total of 61. So that's chopping it up into 4 different trapezoids, finding the area of each trapezoid, and then adding them all together. So that was kind of the longer way to do it because you're literally finding the area of each tiny little trapezoid. I'm going to show you guys with another example how you can just use this kind of master equation up here to find the area. Excuse me. Estimate the area under the graph f of x equals e to the x over the interval of 0 to 1 using 5 trapezoids. So truth be told, I think the problem just kind of cut it off right here. This is all they told you. Over the 0 to 1 using 5 trapezoids. So the first thing you have to do is take the interval of 0 to 1 and split it up into 5 equal chunks. If you divide 1 by 5, that you get 0.2, which means that every single jump along the x-axis has to go up by 0.2. So 0, 0.2, 0.4, 0.6, 0.8, and 0.1. I mean 1. So that's splitting it up into 5 trapezoids. Even though I know it's 6 numbers, but the trapezoids are kind of like what happens in between these things. So it's like 1, 2, 3, 4, 5. Now the next thing we need is plugging in those numbers into the function to figure out what the y value is. So the function here is f of x is equal e to the x. So this first one here would be e to the 0. Then this would be e to the 0.2. This would be e to the 0.4, e to the 0.6, e to the 0.8, and e to the 1. Then if we start plugging that into the formula, we're going from 0 to 1, e to the x dx is about, it starts with 1/2, and then in each interval is 0.2. That's like the height of each trapezoid. And then we're going to multiply that times all of the bases. So the first base is e to the 0, and the last base is e to the 1, which is just e. But then each base in between gets double used. So it's going to be 2e to the 0.2 plus e to the 0.4 plus e to the 0.6 plus e to the 0.8. So when you add all the, well, really it's just all calculator crunchers. So you would just grab your calculator and plug all this in very carefully. And when you do that, you get about, I'm gonna use wavy equals sign, 1.724. Yeah, so that's that problem. Last problem. A cross-section of a river is shown. If water is flowing at 0.8 meters per second using the trapezoid rule with 7 trapezoids to find an approximation for the volume of the water passing this point in 1 minute. All lengths are in meters. So, we've got this, and I did a little drawing here. This river, and we're going to try to find all the area underneath it using the trapezoid rule. So basically, if you need a visual, we're going to be, making a trapezoid here, and then a trapezoid here, and then another one here, and another one here, and then here, and here, and here. The way I think it's best to do that is to take all that and put it into this table here. So I put all the points in a table. Now we're going to find use the trapezoid rule to find the area underneath the curve. So the area underneath the curve is 1/2 times the width of each trapezoid. So each trapezoid is a width of 1. These are all distances of 1. So that'll be times 1. And then it'll be multiplied with the first and last height. So the first height was, let me use a different color, 4. And the last one was also 4. So that's 4 plus 4. But then the ones all in between get W's. So we're going to do plus 2 times all the heights that are in between, which is what? 3 plus 1 plus 0.4. Oh yeah, that's why they gave us the table, like that 0.4. I thought it looked like halfway in between, but here you can see at 3 there's a height of 0.4. Plus 1 plus 2 plus 3.4. Then when you compute all that, you get 14.8 meters squared. So that's the area underneath the curve. Now, that's in this scenario or this problem, that's the land that's underneath the river. The water is what's up here. It's like above that. So what we need to do is take the entire thing. Gosh, I'm using so many colors. Let's get this color. Like the entire rectangle here is 4 by 7. So that's an area of 28. So if we take 28 and subtract out the 14.8, this equals 13.2 meters squared. So that means this area for the river is 13.2 meters squared. The 14.8 was all of the land underneath. So this was all the 14.8 here. Now, the water is passing through that section at 0.8 meters per second. And we're going to find the volume of water passing this point in 1 minute. Well, it's going... So the volume is going to be 0.8 meters per second. So if you take 0.8, and that's per second. So for 1 minute, that's going to be 60 seconds. And then the area it's passing through is 13.2. So this is 634 meters cubed. Because you're dealing with volume. 634 cubic meters. That's how much comes through the river in 1 minute in that cross section. All right, you guys, please ask me questions in class. Good luck with those trapezoids.